Hello, am I audible?
Yes.
Okay, so probably I will, yeah, so I think now it's time to start. Okay, good afternoon, everyone. Welcome to the weekly seminar of Aries. So today's speaker is Harshita Gandhi. Harshita completed her bachelor's and master's from Delhi University. Then she came to Aries and did project under Director Sir for a couple of months early this year. And hopefully she will be moving to UK soon for pursuing PhD in solar physics. So today she will present the work that she did during her visit to Aries. So Harshita, please go ahead and share your screen and you can start presentation.
Okay, thank you. Am I audible?
Not very well, can you?
Okay.
Yeah, now it's okay.
It's okay. Can you see my screen?
Yes, it is visible.
Okay. Okay, so good afternoon, everyone. So my name is Harshita. Before starting my talk, I would like to say that I'm thankful to Aries, especially to Professor Dipankar Banerjee and Dr. Vaibhav for giving me an opportunity to work with them. So I'll just continue with my presentation now. The title of my talk today is Probing 3D Kinematics of Coronal Mass Ejections using Multi-Viewpoint Observations. Okay. So as you can see, this slide contains the outline of my talk. I have divided my talk into two sections. In the first half, I will be giving a brief introduction to CMEs, their significance, how do we observe them, and what are the projection effects. Then I will move on to models which people use to fit the CMEs in coronagraph images. One of such model which I have used in my work is the GCS model. I will talk about it. Moving to the CME tracking and then moving to the source region analysis. So the first half of my talk is related to the second half. In the second half, I will be giving the objectives of my work. I will show what data sets I have used in my statistics. Moving on to some GCS fitting, which I did in coronograph images. Finally, I will show the results and the summary. Okay. In the right, you can see an image. Actually, it is a composite image. It is made in the software visualization tool, which is called JHelio Viewer. This image has been taken, is from a vantage point of a stereo spacecraft. So let me just explain this, what is happening here. So as you can see, a CME is erupting from the solar disk and it is moving to the heliosphere. So what are these different things that we can see here? So the central part, which is the green color solar disk, is in the UVI 195 angstrom. Then this middle part, which is the annular part, is in the coronograph 1 field of view, which spans from 1.5 to 4 arson. The outer circle is the coronograph 2 field of view, spanning the distance from 2 to 16 hours. And yeah, we can see that CME is erupting and it is a pretty huge CME. Okay. Okay, so let's start with the introduction to CMEs. CMEs, in short, for coronal mass ejections, these are these big eruptions of plasma and magnetic field. They erupt due to some instabilities happening in the close to the sun, and then they erupt into the heliosphere. Now, some characteristics about the CMEs. The CMEs can contain mass larger than 10 to the power 13 kg. They can have a speed varying from as low as 100 to as high as 3000 kilometers per second. Also, this width that you can see here is a projected width. I mean, speed, I'm just talking here about the projected parameters. I will talk about what are projection effects later on. So the width of the CME here you can see it's varying from 10 to 360 degrees. So it is actually in the plane of sky. Okay. Of course, the actual parameters varies with in a wide range. These are just the approximate values. So here in the right image, you can see a CME, right? So this is in a LASCO field of view. LASCO C2 is a coronograph, which is onboard spacecraft SoHO. This image is from December 2 to 2002. And here you can see a central circle. So actually the central white circle shows the position of the sun, the photosphere of the sun. Whereas the bigger circle, the red circle, is the occulting disk of the coronagraph. And if we do that, we can see the features in the corona. So we can actually see it here. So this is a CME. Now talking about the structure of the CME. So typically, CMEs tend to follow this three-part structure, but not all the CMEs follow this kind of structure. It depends on how do you observe them. It depends from which vantage point you are observing, how the CME is erupting, right? So this is a limb CME. So it is a limb CME, and it has three distinguishable parts. I mean, we can see it. So if the front part, the bright part is termed as leading edge, we have given a notation. And following that, we have a dark region. We have called that as a cavity. And following that, we have a bulb-like structure, which is glowing, and we call that as a bright core. So in most of the CMEs can be identified using this three-part structure in the coronagraph images. Okay. Now, coming to the significance of CMEs. Why CMEs are important? Why do we want to study them? So let's just focus on the left side image. The left image actually shows the magnetic field lines. The top image shows the magnetic field lines erupting from the solar photosphere, right? So this is just a cartoon image. So I'll just I'm just simplifying this. So the magnetic field lines are emerging out of the sun. When they do, they stretch, and when the opposite magnetic field lines, I mean opposite in direction, they come in contact with each other. What happens? There is a phenomena called magnetic reconnection, which happens. So after that phenomena, what happens? The front part of this magnetic field lines, it is erupted into the heliosphere, whereas the other part is left behind. And what happens to this part? So the leading part, which erupts into the heliosphere, if it is Earth directed, it can cause severe disturbances. So as you can see in the right animation, the CME comes, it reduces the magnetic field lines, which means it is disturbing the magnetosphere. It is causing the failure in power grids, right? It can cause disruptions in our satellites, even GPS signals. So apart from the northern lights or the southern lights that we get to see, there are serious impacts of CMEs which we observe on the Earth as well as in near Earth environment. Okay. Okay, so next in this slide, I want to show how do we observe the CMEs, right? So we have covered what are CMEs, we have covered what is the significance, and how do we observe them now, since we know that they have an impact, a huge impact. So in the above animation, you can see the sun in the center, you can see the Earth if you follow my cursor, and let this animation start again. Okay, so you can see two spacecrafts which are moving away from each other, right? So this is stereo A and this is stereo B. So this spacecraft was launched in 2006 for doing spectroscopic studies of the sun. So the whole point of showing this animation is that there are different spacecrafts. They are orbiting, even they are orbiting the sun. They are looking at the sun. They are observing the sun from different vantage points. Now, apart from these stereo spacecraft, which was launched like in 2006, there was a space there. Of course, there is a spacecraft which is called SoHO. It was launched in 1995, and since then it has given a lot of it has done a lot of CME observations. I guess over 10 to the power 4, even more than that. It has detected these CMEs. So this SoHO spacecraft is actually orbiting the L1, right? So this is at L1 point. And since it is always observing the sun in the sun-earth line, so we can only have a single vantage point observation from SoHO, right? So since the sun is itself a three-dimensional structure and everything happening on the surface is a 3D structure, so we need a proper observation. We need a multi-view observation, right? That is why these two stereo spin twin spacecrafts were launched, and they did the great job. Even Stereo B actually, the data from Stereo B was lost, and we do not have its data yet. And here you can see the in the short table, you can see the instruments with their field of view. So I'll just um, uh, repeat these. So in the SoHO spacecraft, we have LASCO coronograph. We had three coronagraphs, C1, C2, and C3. C1 observed the sun from field of view 1.1 to 3 arcsin, which is not currently the case. Whereas LASCO C2, C3 are still observing the CME, observing the sun, and they have this field of view. Apart from that, Stereo twin spacecrafts A and B have two coronagraphs on board. So each spacecraft has COR1 and COR2 coronagraph. Both have a field of view varying from 1.4 to 4 arcsin, from 2 to 15 arcsin. Now, we all know about Aditya L1 mission. I'll just talk about the coronograph on board this spacecraft. So we have VELC, and this will be actually replacing the LASCO C1. I mean, it has other properties also. I'm not going to go into that. So you can see the field of view, it's 1.05 to 3 hours. Right? So many studies which have been done in the past, they actually lacks the observation part from this particular field of view. And that's where the Aditya will come. Okay. Okay, so now since we have covered that observations of CMEs are done and using multi-viewpoint, so why do we have to do these observations? So as I've already stated in brief, that the events which are erupting from the sun, they are three-dimensional structures. So like observing them close to the three-dimensional structure will give us the true, will tell us the true nature of those events, right? So in this figure, what you see is, let's focus on the middle panel, right? So in the middle panel, you see a CME erupting. So this is actually from the LASCO field of view. Okay. So panel B is taken with LASCO C2 field of view. This is in sun-earth line. So here you are, and here is the sun. And this CME, if observed from stereo A, which is in the third panel, you see that stereo A is here. Okay, so this is from 2011. I think so. Yeah, 2010. So by this time, the stereo spacecrafts have moved apart from each other. And the stereo A is observing the sun. I mean, when it is observing the sun, it sees the CME in the right, in the left side, right? So this is towards the Earth. This is, here is you. Okay, and the same CME, when it is observed from stereo B field of view, is shown in the right direction. Okay, so not just the appearance of the CME. I mean, obviously the CME is appearing differently. But apart from that, you can see it's a different shape, right? So in the center, you can see a CME appears white. It is partially yellow. If you ask someone that what is the width in this direction, he or she might say that it is 180 degree, right? By looking at this image. But if you see here, it is spanning, let's say, 30 to 40 degrees. So this is what is called the projection effects. So actually, these images are in the plane of sky. So when I talk about plane of sky, I mean the plane which is perpendicular to the sun-earth line, right? So unless or until the CME is in the limb, I mean, it also suffers projection effect, but it suffers less projection effects. So what we can do to study the true nature of these events. So as I've already mentioned, we have multi-viewpoint observations going on. People are doing the work. So so the drawbacks, or I can say the problems in this projection effects, are mainly the properties like speed and width, which are projected in the plane of sky. So you don't need these because if you are studying the projected values, they may not give the output. They are not true to the close to the true values. That's why the stereoscopic study is important. Okay. Okay, so now coming to the models. So people have used many models in many past studies to fit the CMEs. It's not just this is a 3D model. There are other models as well. So I'll be talking about this because I have used this model in my study. So GCS, short for graduated cylindrical shell model, it is actually a flux rope CME morphology. What I mean by this is that, since I've already mentioned, not all the CMEs look similar in appearances, right? So this model is based on some assumptions, and these assumptions are like it can work only for flux rope like CMEs, means the CMEs which have a flux rope type of morphology. I will talk about that in a few seconds. And let's see how this GCS model looks like. So in this figure, in the bottom figure, you can see three subsequent images. Let's focus on the image A, right? So in image A, this representation is actually a GCS representation, model representation. It actually has two cones, right? So these are the legs of the cones, which resembles the legs of the CME. And this is the tubular part, or you can say circular front, which tries to superimpose on the front part of the CME. Now, there are certain model parameters which are associated with this model. What are these? I mean, since I have already mentioned that this model has assumption, and it is pretty much believed that CME expands self-similarly, and these things are taken care in this model. How? So you see this circular part, right? So this has a circular cross section here. If you try to imagine it in the 3D. So this has a circular cross section, but it is of varying radius. I mean, as much as the CME expands, I mean, it propagates further, the radius of the circular cross section also changes, right? So we generally term as a aspect ratio. We do not particularly call as a, but we talk about in the terms of aspect ratio. And what is that? The aspect ratio is basically the ratio of the expansion of the CME in this direction, if you follow my cursor, and in this direction, okay, in two orthogonal directions, just to incorporate the self-similar expansion while we try to fit the CMEs. Okay. So the figure A is the face-on view of the CME, as you saw in the second slide. If the CME is viewed from edge on, right? So if you are here and you're trying to view the CME from this direction, you will not see the CME as a three-part structure kind of thing. So you will see a CME like this. So it appears differently. Also, this figure C shows the location of the 3D model with respect to the solar surface. So apart from the parameters like apart from the parameters like the angle between the legs of the CMEs, which decides what will be the width of the CME, how the CME will expand. Apart from the height of the CME, like from O to the leading front, there are other parameters which are called position parameters. So those are defined from the location of the source region of the CME. Okay, because it is the source region from where the CME is erupting. It is on the disk. So uh, studying about these latitude, longitude, and the tilt of the CME with respect to the solar equator will give us a clear idea that how the CME is propagating further in the coronagraph images. So this is also an important part, and this is incorporated in this model while we try to fit it. Okay. In the right side, you can see an image, which it is actually a simulated image. So the model tries to simulate the CME, and then when we fit it, it tries to superimpose on the CME. So this is just a white light image, because CMEs are generally, most generally termed as white light features in coronagraph images. So GCS has models this kind of structure, and below you can see the projected wireframe. So actually these are the projected representation of the GCS model. Okay. So moving on to how do we fit a CME in coronagraph image using a GCS model. So this has been done by me. So this image you see here is taken from 2 vantage points. Okay, so as I have mentioned, that GCS model is a 3-dimensional flux rope model of a CME. Okay, so you can give at least, you can give 2 vantage point observation, you can give 3 vantage point observations. Okay, now since in my work I use the data from 2016 and 17, and during that time the stereo B data was not available, so I had stereo A and LASCO data. So I gave them as input to the model, and I tried to fit the model. Now, since I've already mentioned, this model has its own assumptions and its own drawbacks. So sometimes it's get difficult to fit the CME, right? So here you can see it is a limbed event. So you can easily identify the CME. You can easily identify the leading edge or the cavity and the core followed by the cavity. Okay. So okay, can you see my screen? Hello?
Yes, I can see.
Okay. Fine. Yeah, so the left one is the LASCO C2 field of view, and the right one is the stereo A COR2 field of view. This is a modeling of the 17 July 2017 CME. And when you do this, you can actually see this in a GUI, which is in the GCS model, and you try to change these parameters. So it has 6 independent parameters, which I've already mentioned. You have the longitude, latitude, tilt angle, which are actually the position parameters. And the height, the aspect ratio, and the half angle is what the shape of the CME, you try to fit the shape of the CME in that way, so that you are using all the assumptions which are mentioned in the GCS model, like self-similar assumption. Okay. All right. Okay, so let's talk about CME tracking and catalogs. Now, after we observe CMEs in coronagraph images from spacecrafts, the next step is to track those CMEs and to find the kinematic properties. And this can be done using 2 methods, manually and automatic methods. There are already some catalogs. The manual catalogs are STEREO and this GCS and CAT catalog. So STEREO is actually a 2D catalog. By 2D, I mean that this catalog contains the projected values, the plane of sky values like speed, width, right, or the position angle, like this. And this 3D catalog, which was maintained by the some people. It has the parameters of the CMEs which have been derived using GCS model, and there is also a model called a CAT model other than the GCS model. Apart from that, there is an automatic method to track the CMEs, and so far there is a cactus. Cactus is an automatic method which we use to find the parameters of the CMEs. Also, there is a seeds catalog. So in these catalogs, you can easily find the properties of the CMEs. There are common properties such as speed, angular width, position angle, but there are some parameters which is like not defined in all the catalog. For example, CEDAW has the acceleration column, whereas cactus does not have the acceleration listed in its catalog. Okay. So just mentioning here that in my study, since I am doing a 3D study, but I am also comparing the 3D parameters with the 2D values. For that, I have used the cactus catalog to take the values of the CME parameters. Okay. Okay, so now let's talk about the source regions. Now, since I have already mentioned it somewhere in the GCS model that you need a position parameters, and those you can get from, by identifying the source region on the disk. So there are actually different source regions which are associated with CMEs. Okay, and studying CMEs on the basis of those source region will give us a clear overview that how the CME is, how the propagation kinematics of the CME changes, if it is associated with active region or some other kind of source region. Okay. Now, to understand the active region, we have to first look into what are sunspots. Okay, so sunspots are actually the dark areas. They appear as the dark areas, and you can see here. Yeah. So at these positions, what happens? The magnetic field lines come out. Right? They are blocking, or you can say they are in the way of the energy or the heat which wants to come out of the solar atmosphere in the form of convection. And hence, these regions are much less heated as compared to the surrounding region. So their temperature, I mean, it's not that much, but their temperature is reduced by a factor of 1,000. So if the surface temperature is 6,000 Kelvin, it can go to 4,000 Kelvin temperature for these sunspots. Now, if you look these sunspots, so the sunspots you are seeing here is in the visible, right, in the photosphere. So when you see the exact sunspot at much height above the photosphere into the corona, you see them as a bright points, right? You see them as a bright regions. Now, why do we see them as a bright regions? Now, since I have already mentioned that the magnetic field lines are coming out of these regions, so these magnetic field lines, when they reach up to this height, so the bottom image is from UVI, UVI image, and so when the field lines come to this height, they trap these superheated gases which are present at these height, because at this height the temperature is 500,000 Kelvin. So when these magnetic field lines trap the gases, they glow very brightly, and hence you can see them as a bright regions on the in UVI images, right? Okay, so things we take from here is that sunspots are the visual indicators of active regions. So if you want to know where is the active region, you can see the photosphere, or you can see in the visible light where are the sunspots. Also, the same dark sunspots which you see in the visible light is a very bright active region, which when you see in UV or X-ray images. Also, not all the active regions give rise to sunspots. So sunspot can be associated with the active region, but not all the active regions can have an associated sunspot. Okay, so why I am trying to explain this, because in my study I have segregated the CMEs on the basis of 3 source regions. So let's look at the second source region here. This is called prominence eruption. If you just look at the image in the left, you see a thread-like structure and it is then erupting. So prominences are actually the cool plasma materials which hang in the corona. Okay, their footpoints are attached to the photosphere, and yeah, so you can see them erupting, right? So, and you can also see a CME, right? You can see a CME erupting in the C2, in the coronagraph field. So a plasma is a cool material and it is suspended in a hot corona. And you can see them is in the UVI image, so in the UV light, which is at the 304 angstrom. So from this, I would just want to say that CMEs are not generally, many CMEs are associated with active regions, but CMEs can also be associated with prominence eruptions like this. Okay. Hold on. I think there was a slide. Okay. Yeah. Can you see my screen? Hello?
Yes, we
okay.
can see.
Fine. So the third category, which we decide as a source region, is the active prominences. So I mean, it is basically a prominence, but it's either foot, or you can say it's either the foot point is associated with the active region. So you can see here that the prominence is erupting, and you can see a brightening here, right? So either of the foot points of the CMEs are associated or are near the active region. Okay. Okay, so simply prominence associated with active region, either of their foot points associated with the active region are called active prominences. And you can see them in the UVI 304. You can see them erupting. Okay. Now let's come to the second half of my talk. I've already taken 30 minutes. So the second half of my talk is based on the work which I did. This is the objective, oversimplified. So first of all, I identify the CMEs, or from different research catalogs and research papers, which have already used GCS model in their work. Also, in addition to that, I have done the GCS fitting myself for 21 events, just to increase the statistics. Secondly, by identification, I do not just mean the GCS parameters, I also mean the 2D parameters. So because in the end, I'm comparing the 3D parameters with the 2D parameters. So I have also taken the 2D parameters from the Cactus catalog. So that is the part of the identification. The next thing which comes is the model, because I identified the CMEs and I did the modeling on 21 events using GCS. And after that, the output which I got from the model, I analyzed that. I mean, I derived some parameters and I analyzed their statistics. And then later on, I compared those 3D parameters, which are derived from the model, with the 2D parameters, which are taken from the automated catalog. Okay. Coming to the data sets which I have used. So here in the left, you can see the events with the 3D parameters. As I have already mentioned, that there are many papers which have used this GCS technique, and also there are some catalogs. So the first catalog is the, as I have mentioned, that there is a GCS catalog. So the first and the second are the GCS catalogs. I have taken 119 events from this catalog, 79 from this. So there was a certain criteria to take these events. Also, keeping the first database as the reference, I have looked in the other papers. So if I got the repeated events in these papers, I have removed them because I have already taken them in the first catalog. Okay. And in the right side, you can see the events with the 2D parameters, which I mean the 2D speed and the 2D width. So for that, I have used the cactus catalog, right? And there are some events which are not, automatically fitted by the cactus. So for that, I have used the seeds method. So actually, seeds is also a automatic method. So I have used the seeds for those events for which I did not get the cactus parameters. Okay, so in total, I got 348 CMEs to start my statistics. And yeah, so in total, I have 348 to do the 3D speed and width analysis. But let me point it out here that I did not get the 2D parameters for all the 348 CMEs. Right, so I mean, not all the CMEs. There were some poor events, even they were or they were not fitted in these catalogs, so I had to skip them. Okay. Now, as I have already mentioned, that you can segregate CMEs on the basis of different source region because they have an impact. I mean, it depends how your CME is evolving further in the heliosphere. So after doing that, I found out that out of 348 CMEs, I got 166 CMEs which are associated with active region, 98 CMEs associated with prominence eruptions, and 84 CMEs associated with the active prominences. Okay. Yeah. Okay. So this is not the this is not the result yet. So this is a screenshot of a GCS modeling in a coronagraph 2 image, actually coronagraph 2 and LASCO C2. So I have used the GCS model to fit these two coronagraphs simultaneously, CME simultaneously. So this is, you can see this is a modeling of 4th April 2016 event. It is one of the screenshots from 21 events. And when you do that, and I have already shown the GUI of the GCS, you get the parameters such as height, aspect ratio, right? You get a half angle. So from that, you generate a table like this. So this is the first column is the type, which is the successive images of your associated coronagraphs. So in the successive events, you see the CME propagating further, right? So you see the height varying, okay? You see the half angle. So probably half angle is not changing here because this is a coronagraph 2 field of view, right? I mean, we do not see the width changing in the coronagraph 2 field of view. And there is a latitude here, the longitude of the source region. We also have the tilt. So you can see the tilt has changed a bit. I mean, from 64 to 77, but it's not much. So, and the final column is the aspect ratio. And from the aspect ratio and the half angle, you can find the width of the CME. Okay. All right. So I'll come to the results. Okay, so the first result which I have to show here is the speed distribution plot. Now, why I'm showing this? Because as I have already mentioned, that we are trying to see the projection effects in the coronagraph images. How can we do that? We can see the distribution of the speed. So here in this plot, the x-axis is the speed in kilometers per second. The y-axis is the number of CMEs. So it is a histogram. Now, if you just look at the blue one or the purple one, you see that firstly you see that it is ranging to the speed of almost 3000 kilometers per second. So this is actually the histogram generated from the 348 events, which have been, derived using GCS model. So you see that the speed is varying till 3000 kilometers per second. Now, if we look at the one-to-one, one-to-one 2D parameters. So as I've already mentioned that I did not get all the 348 CMEs with the 2D parameters. So what I am doing here, I'll explain this. So the first one is the 3D. The other two are the 2D parameters. I know I could have compared it just with one 2D parameter. I mean, it's just the same if you see it. So the second one here is 340 CMEs from the stereo A. Okay, so basically I have already mentioned, right? So I have stereo A vantage point, stereo B vantage point, and if you take the CMEs the values derived from only stereo A, you get a single vantage point of parameters. You get the projected parameters, right? So let's look at the histogram of that. So if you see the red one, right? So it's the overlapping histogram. You see that the corresponding the CME, which had a speed of 3000 kilometer, is much less when you see the 2D parameters, right? And it has to, I mean, as I've already mentioned, the 2D parameters are in the plane of sky, right? So they suffer huge, they suffer with projection effects. So what you get is a very lower value of the speed, which you can get by doing a 3D step. So I'm not saying that it is definitely 2800 kilometer per second. It might vary within some uncertainty, but it is still close to the true value because you are doing a 3D study. Okay. I have already mentioned some average values here. I mean, averaging over the 348 events, you get the average speed for 3D average speed as 645, and you can see the 2D speeds are very close to each other, 490. Okay, now so I'm not the only one who did this study. There are many people who have done this, but the thing is that they have not done it with GCS model, right? So this is a screenshot from a paper by Gao et al. Actually, he also wanted to see the effects of projection effects, and he corrected them also, but he did not use the GCS model. I'm just showing this here just to show you that indeed after correction you get the speed greater than the projected value. So you can see in this histogram also for this before correction, the maximum speed which it is approaching is 1200, whereas after correction the speed which it is approaching is 2000 kilometers per second. Right? Okay. There are other studies which have done the speed distribution, but only with the projected values, right? So there is a paper by Gopal Swami, which I have not shown here because it is all just the 2D histograms. Let's come to the width distribution. So while using GCS, I got not only the speed, but I get the width also. So here, the very interesting thing that you can see, I mean, it has to be, because for the 3D events, the CME width cannot go, cannot go beyond 180 degree. So you can see here the histogram for the 3D events, right? For 348 events for the speed, for the width, has the maximum value up to 180 degrees, whereas the same events from the 2D study is going to 360 degrees. As I've already mentioned that, and I showed you the image with the 3 vantage points, right? Where you see an image looking as halo, but it is not halo from different vantage point. So the width estimation is generally overestimated when you do a single vantage point observation. You get these values from 210 and 360 degrees, which are not realistic. Okay. Now, so generally what people do is they try to segregate the CMEs and try to see their width depending on the source region. I mean, there are studies being done, the relationship between the width and the source region. So what I did is that since I segregated the
Harshita,
300.
sorry to
Yes.
interrupt you, but you have only 5 minutes left. So maybe try to wind up soon. Okay.
So in the right image, you can see the width distribution, but only for the 3D case. So what I did is that I segregated the CMEs into 3 different source region, and I'm trying to see if I can see some kind of different width distribution as compared to the overall width distribution for the 3D parameter. But I don't see it much because I don't have much statistics to actually see the distribution in the width. Okay. Now, I have plotted here a true speed versus projected speed. It is actually a good plot because it clearly shows you the effects of projections. So you can see here that on the y-axis is the true speed, on the x-axis is the projected speed, right? And there are two data points. So the blue data points corresponds to the value of the true speed and the projected speed from a stereo A point of view, and the other one is from the stereo B. And we can see the slope also is greater than 1, which clearly says that, yeah, the true speed is greater than the projected speed. Okay. So has been a study which has been done, by Majumdar et al. And they did a separate study, but they also plotted this true speed versus projected speed. Their statistics was 59 events, but you can see, the dotted line is the y equal to x line. So you can see the events located above the y equal to x line, which are showing that the true speed for these events are greater than the projected speeds. And in my case, most of the events are lying above y equal to x line, since I have increased the statistics by a little amount. Okay. Also, there was work done by Gopal Swami. He also wanted to see this corrected speed, apparent speed, but he has not used the GCS model to estimate the corrected speed. Okay. He has used some other geometry based model. But in his paper, it is surprising that he has mentioned that he do not see any correlation between corrected speed and apparent speed, even though all the events are lying above the y equal to x line. And he has given this reason based on the correlation coefficient for this plot. Okay. Yeah, okay, so the final plot, I guess, for my work is to see the relationship between true speed and the true width. Okay, so this is actually, as I've already mentioned, the CME when propagates, it does not only propagate in radial direction, but it also expands in the lateral direction. So the width also increases when a CME propagates, right? So the left plot is the overall speed width plot for 348 CMEs, but as you can see, there is a scatter in the plot, right? So you cannot clearly give the reason that you cannot state that if the speed or width are related somehow, right? So what I did, since I segregated the CMEs, especially for this part, so I saw their speed width relationship for individual source region, right? So as you can see, the blue line, the blue fitting line corresponds to the active region, which are 166, right? And you can see the data points, separating from each other a bit. So this plot shows that with the increasing width, obviously the speed is increasing, but you are seeing the different signatures for different source regions. Okay. All right. Yeah, so just to compare with the previous studies, because the studies have been done with the projected parameters, and so this study is with the limb events. Of course, the projected speed and the projected width. It was done by Gopal Swami, and so I just want to emphasize on this, that the work which I did was to estimate the 3D parameters, right, which are close to much true values, and the past studies which have been mostly done are done using the 2D parameters. Okay, so coming on to the summary part. So CMEs are these 3D structures, but they are projected in the plane of sky. So they give us a false idea about the nature of CMEs. Therefore, multi-viewpoint study is important. Correlating CME speed and width on basis of different source region give us a better idea on the underlying physical process, because as I've already mentioned, the different source regions have their different initiation mechanisms. How the CME will erupt and how it will appear in the coronagraph image, it depends on the type of source region as well. So yeah, even the results which I have shown here, they are devoid of projection effect. I will not say fully devoid, because they are much closer to the true values. And we clearly see a relationship between true speed and projected speed, which confirms the projection effects. Okay, I'm just near the end of the talk. Okay, So this is the ongoing work. Actually, I have already mentioned, since I did the GCS fitting not only in the outer corona but in the inner corona as well in COR1 images. Since we know that CME tends to expand much in the inner corona. I mean, its width varies. Okay, so you cannot plot a speed versus width plot from the in COR1 field, COR1 data. So the ongoing work is still that I am trying to study the CME kinematics in inner corona, since they tend to expand, and I'm trying to see if the radial speed and the expansion speed are related to each other, and how they give us insight to the evolution of early stages of CME. Yeah. Okay, that's it.
Okay, thank you, Harshita. So we have some time for questions. So please raise your hands if anyone has any question. So one question is by Pankaj in the chat box. Pankaj, would you like to unmute yourself and ask question? He's here. I don't know.
Yeah.
Okay,
maybe
maybe.
See the question.
Yeah.
I can see the question. Is the bright leading edge dark cavity bright core is generic feature of all CMEs? What when the ejection is close to our line of sight? Okay, so actually I don't know second part what he's trying to say.
So he's trying to say what will happen when the ejection, when the CMEs are close to your the line of sight. Yeah.
Okay, means it's an earth line. Okay. So firstly, as I've mentioned, that not all the CMEs show this three-part structure. Also, regarding the line of sight, CME propagating in the line of sight, when the CME propagates in a line of sight, it becomes a halo CME. Okay, so basically you cannot even tell what the actual width of the CME is, and you cannot see the three-part structure in that case, because it is something which is coming towards you, or something which is going away from you, right? So you can see the outer part only, and you cannot see the face-on part of the CME. I guess that's what it means.
Okay, so you mean to say it depends on the line of sight, right?
Yeah, definitely. As I've already mentioned, it depends how we are observing the CME, and is it in the limb or is it in the line of sight?
So are there any other questions?
What is the error in the determination of CME speed? Okay, so there is a fitting error in the CME speed. I think here, I think, right? I think he's asking this.
Yeah.
Okay. Yeah. So actually, there is no measured error, but I tried to find the fitting error. So for that, I have used a technique called a bootstrapping technique. Okay, so bootstrapping technique is a resampling technique which tries to find a distribution of the parameter to which you want to find the uncertainty, and from that distribution you can find a uncertainty to 2 sigma or 1 sigma, whichever one wants to, and you can then plot it here. So that's what I have done. I found the average speed as 518, and I found the error in the speed as plus minus 47 kilometers per second. This is the 95% confidence interval. So
how do you get the average speed here with this graph?
Okay, so with this graph, the linear fit is just simply a linear fit which is done, right?
Yeah.
And the average
error,
speed.
How will you do the error here without having the error on individual height points?
Yeah, okay, I guess. I mean, you're saying the measurement error, right?
Yeah. This is the shaded area is the error or what?
It is. Yes, it is the uncertainty in the fitting parameter. So it is uncertainty in the. Yes.
See, until and unless you don't have a error on the individual data points, how will you get the error on the this slope and other things?
Okay. Actually, yeah, that's what I'm mentioning here.
Yeah, same thing here
so
also.
This, So the technique which is called a bootstrapping technique. So actually this technique is used to find the error in the fitting parameter, right? So you see this. I mean, this is
I understand this is bootstrapping.
Okay, that's how I found this 2 sigma error from this plot.
2 sigma.
Yeah, this is 95% confidence interval, so sigma either side.
Why you are quoting the 2 sigma? Is sigma is not enough?
Okay. I think it because it is the confidence level. I mean, by quoting 2 sigma, I can say
Usually you quote sigma level. That's what I'm asking. Why the 2 sigma? Yeah, one thing is that your distribution is not symmetric around the central value.
Yeah.
Probably this may be the reason, but I'm not sure. Okay.
Okay. Any other question? Okay, then I have a question. I'm following up on what Jeevan sir already asked. So the error in the individual, measurements will depends on how well you fit your GCS model in coronagraph images, right?
yes.
Because those values are derived from the fitting of GCS model. Now, coming to the fitting of GCS model, can you go back to the slides where you have fitted the wireframe in green over coronagraph images? Yeah. So in this, so in fact, before that also, you had one image where you showed the GUI and several, independent parameters. So in that, this one, this one. Yeah, so you see that you said that there are 7 independent parameters here.
Yes.
So if there are 7 independent parameters and you need to determine them uniquely, so in that case you need at least 7 pieces of information. It's like I mean in a mathematical sense, if there are 7 unknowns, you need 7 equations, and equations. Yeah, so 7 equations are a mean of you can say 7 different pieces of information. So here you have only 2 vantage points. So I'm just wondering, I mean, how did you fix other parameters? I mean, you are deriving 7 unknowns with just 2 pieces of information. So how did you, I mean, how confident are you that these parameters are not degenerate and they are unique?
Exactly. One way is that one can try to fit the same CME again and again and try to see the the model parameters which one is getting after the fitting to avoid this degeneracy. And
no, what I mean by degeneracy is that let's say your height is let's say your tilt angle is 4.5 and your ratio is 24. I mean, you can get the similar type of fitting with tilt angle, let us say 14, and the ratio to be, let's say 10, something like that. So this is what I mean by degeneracy. So how will you break this type of degeneracy in case when you have less information than more unknowns?
Okay, so I mean, one way is one can try to fit more observations from more vantage point. That is the one way, right?
Okay.
Here I have used 2 vantage points only, and yeah, I mean, I totally agree with this that I'm using 2 observations here, and I'm trying to estimate 6 data points. But yeah, I mean, at some place one has to look into these parameters while doing the fitting. So generally, I have seen while doing it that the latitude, longitude do not change much. Okay, they try to remain constant up to 2 decimal places. Then if I talk about the tilt angle, so since my study is generally, this flux slope model, the GCS model tries to fit the height of the leading edge, right? Yeah, it definitely taking into account the tilt angle, but the angle which I give in the beginning is by looking at the source region, right? So and I see that I look at the movies and I see that the CME is not much changing in the orientation.
So there is a question on similar line by Kuntal, and she's suggesting that can some of the parameters be fixed while doing the fitting, like latitude and longitude? I mean, you do not change them later on, and I mean, will that help you to get a unique solution or something?
Yes, definitely. I mean, if you are trying to reduce these degrees of freedom and you try to constrain them, it will definitely give the better height if I'm trying to find the height.
Yeah, but Harshita, I'm wondering, I mean, you said that you have this source region information, right?
Yeah.
So if you have source region information on the sun, I mean, can't you fix latitude and longitude looking at the disk?
Yes, so, one can fix it.
Yeah.
That's what I have done.
Okay.
Yeah, I will just add at some point in this discussion. Yeah, so you have used those terms properly. So basically, as you mentioned, you have to constrain all the 7 parameters are whether they're free parameters or not. You have to check that, and as many parameters you can constrain. Maybe some parameters are dependent on each other. That also one can identify. When you have such a number of parameters, you have to try to constrain and see, but it is not a unique solution at the end of the day. You will definitely find other permutations where you will get the same result. So one has to find out which are those parameters which are independent and which are dependent. So that kind of, and of course, if you have more vantage points, as you rightly pointed out, you can constrain things better. The other thing which I think this discussion was going on about the errors, right? So as I think Vaibhav pointed out, so here you have to find out that it's basically your selection to some extent. So what is the resolution of your selection of your image and all that? So that also tells you about the errors in each point. I mean, if it would have been an observational thing, your resolution of the imager would have given you a limit, right? You cannot differentiate between a sub-pixel level. So your pixel size will give you uncertainty, because at the end of the day you're clicking it. So those kind of estimates also can be helpful. You can think about it in that way. It's difficult to quantify them, but you should know priori, your uncertainty from that angle as well.
Yes, I mean, even in the GCS model itself, there is a thing called goodness of fit parameter. You try to manually make contours around the CME, but that is again you are doing manually, and you're trying to see how best the GCS has fit the CME and how you have drawn the contours. So it compares the both and gives some percentage. One can also use those.
GCS also takes care or inputs in terms of your cadence and the spatial resolution. Does it take, is there an input somewhere to sort of determine this goodness of fit and all that?
No. Only just these parameters which are mentioned.
I see. Because it should come some way.
Yes.
Okay, do we have any other questions, suggestion, comments, criticism, anything?
I just wanted to ask a quick question. So
yeah, sure, please go ahead.
Algorithm is it using to calculate the goodness of it while doing the minimization and the fitting to give the best fit parameters?
Actually, I did not hear the first part.
Yeah, I was just saying that how is it doing the minimization and giving you the best fit?
Okay, this model. Yeah, so it actually what it does that you have a manual control and you draw a contour. So like it is fitting the CME with this green wireframe, and depending on that, it is giving me the I do the best fit and I get these values. But when you try to find a goodness of fit, so let's say I did the fitting and then in the next step I do that goodness of fit by drawing a contour manually. But that is manually. I mean, you cannot draw a perfect contour also. It will distort. So if one can try it multiple times, I mean 5 times, one can draw the contour and tries to see the match between the modeled this green wireframe and the contour one. So it is basically comparing both the fittings. I mean, so I did not find much use of that error. So that's why I did not incorporated that in my study. Apart from that, I did the fitting error using Bootstrap. found that much.
Yeah, just for the point of discussion, I mean, I think it's a good thing. Since the goodness of fit also will probably look at subsequent images and fitting also. It's just not one, because
Yes,
that's a sequence of images. It's a movie frame. So that's why I was mentioning that somehow the cadence and the spatial resolution has to come in some way in the goodness of fit. I do not know the particular tool. Ritesh or Shatabdo, do you have idea how they have done the goodness of fit?
Actually, Deepuja, this GCS treats individual frames as like separate quantity. That's why this cadence information we cannot provide while like time series analysis.
I see.
And for this goodness of it, they use some iterative methods to match the outer contour which we have provided manually with the GCS fitted this outer boundary. So it's an iterative basis for getting this fitting.
So ideally, they should use subsequent images to also constrain things, because in one frame, they do not have that much of information as compared to, because the CMEs also is propagating, of course. Then you need the initial some input for the speed and all that also, which probably you are not doing.
I think what they are doing, Tibuda, here is that they wanted to give an estimate on the they want to give an uncertainty on the location of the leading edge, and that is it. And for
so
that you do not need
only they can talk about
only on the leading edge in the spatial direction. I mean, for example, in her plot where she has only individual point, you will get errors in the vertical direction only on the y, not on the time,
not on the x.
Yeah, so that is what it is. I mean, that the goodness of it will do.
Okay, so that's not enough. So it's better to do subsequent, at least, some answers. So Bootstrap is providing you a little bit better, sort of at least range of things to believe.
Yes.
Yeah, you have other thing is that you have a spatial resolution. So based on that, we cannot do the goodness of fitting and all that.
That's what I was guessing initially.
Yes,
but
it can be done, sir.
It
can be done. I mean, previously when we were not using GCS, I mean, long time back when I was doing CME studies, we used to capture the uncertainty in the location of leading edge using the information of spatial resolution, as well as how fast the intensity decreases when one moves from inside of CME to outside. So that is not a step function. That is like a sigmoidal function, and then one can calculate that number. So we did that a long time back, but yeah. But she has not implemented it here.
Yeah, these are ready tools,
No, yeah.
So Harshita, there is another question from Prajaval. Question is, can the principal component analysis, PCA, can be used to freeze some of the dependent parameter? So am I right? You mean
I think
principal component analysis, right? I believe it is so. So can you do that?
I don't know what is PCA analysis.
Yeah, to some extent, I think it can be done. It depends on, I mean, in PCA, if you do not have some parameters which are not changing much, I mean, that will not come into account. So yeah, that can, I mean, it is a way to reduce the dimensionality of problems. So instead of 7 dimension, you can still work with like 2 or 3 dimension, which determines best where the CME is. So probably maybe if you do the PC analysis, maybe the tilt angle will go away, because I mean that dimension will be reduced in my experience. So it can be done, but still I believe you need more and more vantage points and more information in order to further constrain the CMEs. Yeah, but that is a good suggestion. Okay, any other question?
Okay, I have a concluding remarks. I mean, all the best, Harshita, for your PhD and further career. Hopefully, you'll be able to travel soon. Yeah, and in fact, for academic committee members, I sort of informed that all the project students who are doing projects here, even remotely, I think we should have their seminars scheduled at some time. So again, colloquium committee, it is your responsibility to coordinate with the academic committee to know who are the students who have been doing projects last 6 months or so, and then organize the seminars. Okay.
Okay.
Shall I stop sharing?
Yes, I think we are done.
Thank you.
Okay, then we'll meet next week
Yeah.
at 3:30 for another seminar. Thank you for joining.